The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to Stats for the Masses webinar, overview of multiple regression. I'm glad you guys made it today. My name is Elaine Eisenbeis. I'm the owner and principal statistician here at Omega Statistics. I know many of us are busy with the holiday season, so I want to thank you who are attending for taking the time to join us live. And in fact, I want to thank everyone for their interest in our webinars. I really enjoy putting these together, and I like the time we get to share every month. So I have a little bit of a cold, a little allergy or something today, so bear with me, and I'll try to be as clear and concise as I can be. Today, we're going to present a very simple overview of multiple regression. It's a pretty involved technique, but I'm going to do my best. So I'll start with some review of some math. Some correlation. If you attended the correlation webinar in October, we're going to be using the same data set, and we're probably going to take some of the correlation and work with that. And then I'm going to demonstrate how that relates to a simple regression, and then finally we're going to work through a multiple regression together in SPSS. Today's just an overview, but I hope that the information you receive today will give you some ideas and guidance on how to make use of the multiple regression in your research. And I say this in all of our webinars: use what you learned today, apply it in a holistic way. Think about the big picture, not just the how, not just the little details, not just where did the numbers go, but why. What did the numbers mean, and what does it mean to your research? And as always, it's my hope that if nothing else, you're going to come away from today's presentation feeling a bit more in control of your capabilities as a researcher, at least feeling that you can do it if you work at it, right? And that's how it is with things in general. So this webinar may be a bit longer than most, depending on how well I navigate my computer and my screen. I'm going to try to show you some examples. So I anticipate about 50 minutes of the presentation, and that'll leave us hopefully about 10 minutes for some Q&A at the end. And right now I've currently muted the line, so only my voice can be heard, but our assistant statistician, Brianna Ramirez, is monitoring the chat board. So feel free to type any questions you have on the chat board, and Brianna will choose some to ask me at the end of the presentation. She'll also try to assist you with any technical problems you may experience. If you find you have any technical issues, I often find that just logging out and back into the webinar clears up just about everything. So I always say, when in doubt, reboot. And so let's go ahead and get started. So before I begin, I'd like to take a little bit of time and tell you about Omega Statistics. You see this slide probably every time, but for the people who are new, it's just nice to know a little bit about where I'm coming from and how I think on things and what we can help with. After the webinar, I'm going to take some time to tell you about all of the new happenings here at Omega Statistics and with the Stats for the Masses webinars, newsletters, upcoming workshops. I'm pretty excited about 2015. So that's great. My goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate about statistical concepts in a way that we can all understand. Sometimes that's not easy, but we try to do our best so that everyone can see the elegance and usefulness of statistics. So we're a private practice in Southern California. We handle both medical, clinical research, clinical trials, journal articles, helping with those. Methods, results, design, analysis. We help with epidemiology studies, large data sets. Exploratory design and predictive modeling, and actually multiple regression is great for predictive modeling. In fact, that's what's used. We do help with the dissertations. We help with the methods and the results chapters. We can help you with survey design. And we handle projects of any size, from projects that take an hour or two up to months, So, yeah, we do quite a bit. Our motto is to provide elegant solutions effectively applied. Okay, so I'm going to take a little sip of water, and then we will get into this. Okay, so what is multiple regression? Usually I like to pull something out of a textbook and then also give one of our definitions. Well, this month actually I found a great definition from the freedictionary.com online. multiple regression is a statistical technique that predicts values of one variable on the basis of two or more variables. And that's a pretty darn good definition. And so we're going to review a little bit, and we're going to get prepared. In our October webinar, the correlation webinar, we covered bivariate correlations, and we tested the association between two variables. Are they moving up together? Are they moving down together? Are they moving in opposite directions? And it was between two variables. A simple regression can be derived from that correlation. In a simple regression, one of the variables in the correlation would be used as a predictor to predict the other variable. And so X is usually what we call the predictor, and Y is what we call the outcome or the criterion variable. A multiple regression can be thought of as an advancement beyond a simple regression where we include more than one predictor, but we still have only that one outcome, only that one criterion. So all the predictors, there's a way that they're added up to come to that score or the outcome measurement of the criterion. A multiple regression is usually much more informative than a correlation or a simple regression because more often than not, an outcome is made up of more than one thing. I think of it like a recipe. You have a lot of ingredients to make a cake. Some ingredients are more important than others. And so we're going to make our own little cake today. So, of course, we use math to help us understand the concept of a regression. So bear with me, and this is recorded. You'll get a copy of the recording so you can look at it again, maybe, you know, if you have a little bit of trouble now with it. But sometimes this stuff takes a while to sink in. However, if you are familiar with the equation of a line, you're going to have a lot easier time understanding a regression. This is the slope-intercept form. Y equals mx plus b, and it's the slope-intercept form of a line. The way it is, it's set up on your little axes here. Here's your x, and here's your y going up, okay? And a line is going to connect some points for you in math. Well, here's your slope is how basically the angle of your line. Is it going more straight? Is it going more flat? You know, is it going up? Is it going down? That's here. Your intercept is this little guy out here all by himself, this little v. And this is your y-intercept. So since this is your y-axis, here's where it's intercepting, right here at that point. So that's where the line intercepts your y-axis, okay? Y actually is going to be the other part of x, because to have a line, you have to have points on the line. Every point has two values. It has your x value and your y value. So let's say, for instance, here's your x equals 1. And if we go up here, you can go across to your y equals 3. So your point right here is going to be 1, 3, right? 1, 3. So that's kind of the general idea of a line, okay? So let's go on to the next one. The line for the simple regression model with just one predictor, remember it has just one in the simple, it's very similar to that slope-intercept equation of a line. The difference is that the slope-intercept form of a line is exact. All of the data fit the formula perfectly. So if you look at this line here, there's no data off here, there's no data up here. You can't see the points in this graphic, but we're assuming every single point you ever want using a particular equation is going to be on this particular line. Okay, once you fill in those numbers for your x's and y's and your slope. So the difference is that the slope-intercept form is exact. But in statistics, our line is called the best fitting line. And we need to accommodate the variability in the data you collect. So we add an error term, which is this little epsilon. We add that to your model. So, and of course we have to change the letters because we have to make it confusing because that's statistics. So we would change the order of the terms also a little bit. So right here, here's our outcome, here's our criterion. Here would be our little predictor right here that we're using for the outcome. And then right here's your error, okay, and here's your intercept, okay, and here is your slope. Okay, so it's kind of the same format, and I'll show you. You can see how they match up. The error term's the only difference. Okay, the nice thing about the ordinary least squares regression is that, and that's the multiple regression, it's just another name, it's a type of way of looking at it, is that when you do your computations with your data, the error terms add up to 0. So that means we get rid of that error term. And we won't be doing that math today. However, I'll show you a little bit. When I go through it, you'll see what I mean. It's how they would go to 0. But here they are. Here's your y. Here's your slope. And that's actually supposed to go over here a little bit more. Oh, no, there's your x. Well, here's your slope with the x there. So here is your slope. The x stays the same. The y stays the same. Here's your intercept right here. Okay? And there's your little epsilon, your little error. Here's a visual. Oh, okay, good. I put one in there. Here's a visual for why we have the error term in theory and why it can be reduced to 0 in the ordinary least squares model. These are data points plotted for two variables, like a correlation in a scatter plot. If you remember from the correlation webinar, we had the scatter plot, and then we could see if they were going up, if they were kind of going down together, things like that. So here's our scatter plot. Here's our regression line, okay? And remember how I said in math, the slope of a line is exact. Well, here it's not. See, there's some above it, there's some data points below it, and these are all those little XY values, right? So here's when X is 60, your Y outcome would be somewhere around, I don't know, 140 or so, you know, so every little point, every little data. And so what we do with the regression is we draw the best line we can in between all those data points. So as you can see, you should have in the best of worlds, in the best case scenario, half of everything would be above the line and half of your data points would be below the line, and you'd kind of be equally above and below. So this guy here is about equally below, this one's equally high. All the data points above the line, these little errors, these are your errors, these orange lines, because that's, you know, your variance also, it's called. How far are you away from the line? If you're above the line, it's positive. If you're below the line, this would be negative value, so it would be negative whatever number. So if you have your positive here, your negative here, they're going to even each other out. That's how your error term disappears in a regression, and that's what you want. And the reason is if you fit that line directly in the middle and you have half up and half below, they should equal. That error should go away because you have the equal number here, positive and negative. Okay, so goodbye error term, and that's where it goes. And that's once you plot the data. Finally, since we just don't have enough equations, we need to have another one to work with the data. And this is just how we are. We have to have Greek symbols to represent the true parameters we are guessing at, because we never know the true parameters. If we knew what the true value here of your coefficients were, what you needed to multiply by your predictor to get your outcome, because you're fitting that line, then if we knew the truth, we wouldn't need to estimate it. Okay, so when you have these Greek letters here, these are the things you're trying to estimate that are, in fact, the true things that you never know. Then what we do is we go out and we collect our data, and then we have statistics. And we also call them parameter estimates because we're estimating these things with the data that we pull. So whenever we do that, we use Latin. So we have regular letters here, A's and B's and Y's. Up here we still have our Y's and our X's because actually these would be data. But here we have actual letters. So we kind of use this whenever we're making our predictive equations. So remember, the error term's gone by the time we make our estimation model from the data that we collect, because that line is going to be fit right in the center and it's going to make everything zero out. Oh, so we have a lot of assumptions. As you have to assume a lot of things. Your data's not lining up nice and pretty on that line. It's scattered about it, you know, so you need to make sure that you're going to have a way of making that line fit in the middle of the data. Depending on your reference, whatever book you're reading or whatever website you're looking at or whatever professor you're listening to, the assumptions for regression can be many. Many texts will state that a normal distribution is needed for the criterion, and that's good to have, but it's not absolutely needed in many cases. It is needed, though, for the multiple regression we're looking at today. But there are other types of regression where you can use data that's an outcome that's a 0-1 or a count. You might have heard of them. They're logistic regression, Poisson regressions. But today we are going to use the multiple standard ordinary least squares equation of a regression where you do need that continuous outcome. Another assumption often mentioned is that the observations need to be random, and that's rarely the case. In the best of all worlds, you will go out and collect a random sample, but in most disciplines, social sciences, behavioral sciences, things like that, usually you use a convenient sample, and the regression holds up just fine. But here are some of the assumptions. These are the 6 ones you see the most. All of your variables should be continuous, both the predictors and the outcomes. There must be a linear relationship between the predictors, your X's, and your criterions, your Y's. You should have a normal distribution for the criterion variable, which is your outcome, which means if assumption 3 is met, you should also not have outliers. Your data needs to show something called homoscedasticity, and that's that distance of the errors from the regression line must be similar. So your distance above the line of all your errors and the distances below your line of all your errors should be similar because you want them to zero each other out. And the errors, they must be independent. They need to have that mean of 0, a common variance, and normally distributed. And I'm going to show you this on number 6. It's when you see it visually, you'll say that's it. It sounded so complicated. It's really not. And hopefully I can show you how it all ties together. There are 2 big assumptions that you really need to have in order to be close to fitting a good regression model with your data. The other ones can be relaxed here and there, aren't all that important. If these 2 assumptions are met, you're doing pretty good. And the first one was the second assumption we looked at, where there must be a linear relationship between the predictors and the criterions. And this is seen in the equation for the regression because it's an equation of a line, and a line is linear. There's no little humps in it, no little bowls. It's not parabolic. It's just a straight line. Okay. And now the residuals of the regression line must be independent and with a mean of 0, common variance, normally distributed. That's what I said sounded really, really confusing. And like I said, I'll show you that. And note, assumption 1 is inaccurate. It said all of your variables should be continuous. In a regression, your predictors can be just about anything. You just need to accommodate them. They could even be categorical, and then you can use dummy codes or indicator variables to break them up. And I showed that, I think that was in the February webinar, the GIGO no-nos. And you can go back and look near the end of that, and I show you how to clean them and code them. I think I did it for ethnicity, gender. So definitely you can use for a predictor just about anything. In the regression that we're looking at today, the standard multiple regression, your outcome does need to be continuous. All right, so wow, we're already going to look at the data. Maybe we will get done faster. So we're going to be using the clean data set from our data cleaning webinar, which I just mentioned, the one that we did in February. And we also use it in a correlation. It's the biofeedback data. And we were looking at biofeedback as a stress relief technique. It had 112 people. They were divided into 2 groups. Okay, the experimental group were given biofeedback training, and there were 51 of them, and then 61 in the other group who weren't giving a biofeedback training. They took a stress measure before, and then the treatment group went into the training and the control didn't, and then both of the groups took the same measure after to see if their stress decreased. Okay, because higher scores on the stress scale, this perceived stress scale, higher scores are associated with higher stress. Okay. We also collected some demographics. We collected demographics for age, for gender, for ethnicity. We asked participants if they ever had received biofeedback training in the past. What we're going to use today are these ones. We're not going to use all the variables, but we're going to use age, which is the participant's age in years. We're going to use their pre-test score, and we're going to use their post-test score. We're going to use gender, and when we coded this is your dummy coding. We made the males 0 and the females 1. So our reference group is the one that's coded 0. So our model that we're going to make with the regression is going to be in reference to males, and then we're going to look and see if there's a difference for the females when compared to the males. Our participant group also is a dichotomous variable. We coded it with the control as 0, and the experimental group is 1. So again, for the model, we're going to make it where it models the control group, the people who did not receive the biofeedback, and we're going to look and see if there's any kind of significant differences for the experimental group in reference to the control, when you compare it to the control group. Okay. So here we have the correlation, and this is a correlation of the pre and post intervention stress score. Okay, let's go ahead and do this. Let's go in to the data set, and I'll send you a copy of the data set so you can play with it. So let's go ahead and run a correlation. So we'll go up to Analyze, we'll go to Correlate and Bivariate. And I can't remember, I think well, since it is a regression, you really, for your X variable, since that's your predictor, you want to see if the pre-test scores are a good predictor of the post-test scores, not the other way around. So let's make it, let's go ahead and put these in and see if they come up correctly. So here's the score at time 1, here's the score at time 2. And then we'll just click on OK. And there's our correlation. Let's make a scatter plot. So we'll go up to Graphs, and I'm going to go down to the legacy dialogues because I'm used to doing them the old way in SPSS. We're going to go to Simple Scatter. We'll define it, and here's where we'd like to define it. So let's go ahead and do this. Here's our time 1 score, and we'll put that on the X. Here's our time 2 score, we'll put that on the Y, and we'll just click OK. And there are a lot of other options, as you saw, that you can put titles in and such, but we'll just keep it simple for today. Well, we have a nice positive correlation here, very strong one. It's significant. As you can see, the p-value is less than 0.05 if you're looking at a 95% level of significance, which is what we usually look at. We want that p-value less than 0.05. So it's very strong. And here you can see it. You can see where that line's going to go right in here somewhere, right? It's going to go right in here. And so you can see it's positive because it would be an upward slope. You can even click on the graph, double click on it. And you can go right up here. And here's the add to fit line. There it is. This is our regression line. And as you can see, a lot of it's above, a lot of it's below. Here's the regression equation. It's kind of hard to see, but there's your intercept. It's y equals 2.98, and then here's the slope, 0.77, and then that would be your x. So your x is your pre-score, and your y is your post-score. Here's your intercept. Should be coming in down here lower, 2.98. It looks like it's close to that 10. So maybe if we were to bring, oh, you know why? Look at this. This isn't at 0 because you would want your origin right here to show. So let's see if we can change this. I think we might have a little time. We can do this. Let's see. Go over here. Here's the minimum. Let's make the minimum 0 and apply. There it is. Much better. Okay, so now we have the zeros here and we have the zeros on the y. So 2.98 makes sense now. Okay, that is there because there's our 10. So it's about 2.98. Okay, and then our slope is 0.77. Okay, so you could use this equation if you had an x value and you could say you put in a 20, you would multiply it by this 0.77, then you would add the 2.98 and it would take you up to wherever your y needed to be. So probably whatever this point is, right? So you would do the math. Let's go ahead and let's see. Let's pick a point here. Well, let's say 20. Let's go ahead and say 20. They had a 20 on a pretest score. So we'll take that 20 and we're going to multiply it by the 0.77. Then we're going to add 2.98. And I got 18.38. So if we were to go up here, it would be up around here because this is a little higher than 20. So that is how you do this. And then the linear up here is your R squared. Your R squared is a measure. I didn't really talk about it too much in my notes today, and I'll cover it briefly. Like I said, there's a lot to look at in a regression. Your R squared value is the amount of variability in your outcome, your criterion, accounted for by your predictors. Okay, in this case, we only had one predictor. So the predictor of pre-score contributed about 47% to the outcome of post-test. So that's very good. And you would expect that. I mean, people who are scoring low on the pre-test, have low stress to begin with, probably aren't going to increase. And the people that have high stress, they might decrease a little, but you wouldn't expect, unless it's a really, really good intervention, you'd probably expect them to be similar. Now, if it was a really great intervention, then you would expect to see differences between the pre and post. But that's how that would work. Okay, so let's go ahead and go back. So I showed you this, and here's the correlation. If you take this correlation coefficient on a simple regression, it's the only time it'll really work, is you take this 0.684 and you square it, you're going to come up with that R squared, which is pretty cool. So if I take this 0.684, multiply it by itself or square it, I'll get 0.467, which is pretty cool. And these are things that you can use and maybe look up some of your sources and such, and see how that plays together, and more about the variance and how it contributes, because you want to try to account for, you want that regression line to account for that variance, right? You want it to be a really good fit and to be a really good model, and to account for that. If it doesn't account for much of your variance, then you're really not, none of your predictors are really contributing much to that outcome, and that's the big thing about it. So here we are where we fit it, and here's our equation, and there's our R, which is basic, that's our correlation coefficient, right? And here it is squared. Okay, and then here's significance here in the regression too. Okay, and here's our coefficients. So we'll go over this a little bit more. So we fit the line through the middle of the data as best that we could. That was the line of the best fit. And there's our equation that we had. So if we interpret it for our study, we have the following. Y is your post-intervention stress score, equals 2.98 plus 0.77, and your X term is your pre-intervention stress score. So you just kind of plug that in there, and there you go. Using this model, we can plug in a value for the pre-intervention stress score, and we can find the average post-intervention stress score for all of the participants. Okay, so you would plug in your values over here, and you would get your average score for everybody. There are also ways you can use another to predict a score for one person instead of for an average, and then that's where you use your prediction model, and you have prediction intervals, which are bigger than the confidence intervals we might see today, and that's something else you might want to look into. But what we're looking at today with the model, it's an estimation model for everybody. So on average is what your outcome is going to be, your average score for everybody. And so let's go ahead. If we plug that in, say we had a pre-intervention score of 25. So we put it in there. We multiply it by that. We add this to it. Our final score for the post-test will be 22.23. And it indicates that the post-intervention is lower than the pre-intervention. And that's what we wanted. We wanted the stress to go down. So that's a good thing. And the next question is, well, is that significant? And we will look at this a little bit more. So let's look at the multiple regression. Finally, yay, we get to look at the multiple regression. So let me take another sip of water. And the multiple regression is a regression model with more than one predictor. Okay, it isn't easy to show the correlation in a scatter plot now and the line. We'll still be able to see the line, but we won't be able to see like the bivariate, because it's now we're in a bigger dimension, right? After you get past 3 dimensions or so, you just can't really see things visually. We have more than 2 variables in the mix. So it's going to be hard to see that. However, the use of the model for estimation of the average post-intervention stress, it's going to be very similar. But we'll include some additional predictors now. So we're going to keep our pretest score, okay? Then we're going to put in their age. We're going to use gender, and we're going to use participant group. So now we have 4 predictors, So the model is going to look really, really similar to the simple one. It's just going to have a few more B's and a few more X's. Okay, so here's our simple one, and this is the one that when we're using our data, and we have our nice letters that we know. You don't have to. I have a thing on the website saying I wanted to be a statistician because I wanted to learn the entire Greek alphabet. In this case, you don't really have to because you're working with data now. You don't need to know too much Greek. When you're working with the real statistics. And now here's a multiple model. Here's how it would look in theory with your little error here, and here's our four betas. These are called betas. And then our 4 X terms. So one, depending on which ones we put in, one would be for age, one would be for gender, one would be for their group membership, and one would be for the pretest. Okay, and here it is here in nice little terms that we know how to work. Okay, and no error because it's zeroed out. At least that's what we hope. Okay, so let's go ahead and run that, and let me go ahead and pull my notes, and I'm going to show you how to do it in SPSS. If I can put my glasses on here. Okay, so let's go back into the data. All right, we're going to go up to Analyze. Now we're going to go down to Regression. We're going to go to Linear. The dependent variable is going to be our post-test score, time 2. And then for my independence, I'm going to put in my predictors. Time 1. I'm going to put in gender. Now let me see, how did I do this? Did I do it with the time? Okay, first I want to do it the exact same way as my notes. So you can actually put them in here any order you want. But sometimes, when I'm making tables and such, I go, okay, how do I want the table to be laid out? And then I'll run the model that way and put the predictors in the order I want to put them in the table, because it's so much easier than trying to go back and forth and check things off. Did I catch that? Did I do that? So in the model I made the other day, I put the pretest score in first. Then I put in age. So let's go ahead and put in age. And then I put in gender. And then I put in group. Okay. Now over here there's some other options, and I'll go through the ones that I use, and there are many more, but these are the ones that I usually look for. I want to go ahead and get those estimates. I want to get those confidence intervals. Okay, I want to look at the descriptives. I want to look at the part and partial correlations. I want to make sure that none of my predictors have multi-collinearity, and that's whenever their correlations are very, very high, like over a 0.9. If you have two, and it's the predictor variables. If you have 2 predictor variables that have a correlation above 0.9, then you might want to think about taking one of them out, because in essence they're measuring the same thing. You don't always have to. Sometimes you might have a good reason for keeping them both. However, it does play havoc with the model oftentimes. I also kind of want to look at these. We're not going to look at them today, but definitely we'll look at some residual plots. So I'm not really going to look at the numbers. So let's look at the plots. Here's the member assumption number 6. This will help us with this. So for our Y here, I want to put in the residuals. And I want to put in the Z residuals. This means standardized. These are the numbers that have been standardized. So you have a Z score, and that's why they have that little Z in front. And then I want to put Z predicted. I want to make them my X. And I want to look at a histogram. And I want to look at the normal plot too. And that'll help me to see that my model was a good fit, that my errors were basically equal, and you'll see how that works. So do I want to save anything? I'd like to save Mahalanobis distances, and we won't look at that too much today, but that might be something you want to look at. If we wanted prediction intervals, we would ask for them here. Remember how I said if you're looking for one person, that's when you have your prediction variable. If you say, I have a score for Joe, his pre-test score was 25, what would I expect his post-test score would be? This is what you would want to use. You would want to use these individual prediction intervals for him, and you would ask for it, and you would see that it would be bigger than that 95% confidence interval. So we're not going to worry about that today. I just want you to know that it's there. I usually say exclude cases pairwise. And I don't know if it's really necessary here. I don't know if I've ever discussed this with you before, but listwise will take that record totally out if they're missing anything. This one will include it for some, and if they have the data, it'll include the record. If they don't have some data for some type of analysis, it'll take it out. In this case, it doesn't matter because we're only doing one regression model, so it'll take out a case because if it doesn't have any data on it, if it doesn't have any data on a certain case, it'll take it out anyway. But I'm going to click pairwise. And I don't think we need here, I don't think we need this one. I don't look at style too much. So let's go ahead and click OK. And it'll run. Okay, so here's our regression output. Here's our descriptive statistics. So up here on here's how many were in there in the model. So it looks like on group, we're missing a record. They mustn't have had a group coded in there. Okay, so the other ones though all had 112 records. So basically the regression model will make use of 111 records. Here's our mean scores for each of our variables. So the mean age is 19 years, almost 20. Since these are coded zeros and ones, basically they're just percentages. So it'd be the right here. It looks like we probably had a lot more. What did we code? Females as one, so we probably had many more females than males. Here they were pretty evenly divided between the groups. And then, but here up here is your pre-test score. And as you can see, your pre-test score had a higher mean than your post-test score. So perhaps that intervention might have worked. But this is for everybody, right? So when we do the regression, we put group in there. So we'll be able to see if the experimental group was different because we coded them to be experimental control. Here's our correlation table. Okay. And it's basically just like you saw 2 months ago. And it's there for all the values. This variables entered removed just says these all were entered in on one step. There are other types of regressions where you can have more than one step called hierarchical regressions. Sometimes I call them stepwise regressions, but then some people say stepwise isn't the right name because that's another type of regression. That's the problem with statistics is we have 5 names for everything, at least 5 names. I mean, even for multiple regression, OLS regression, multiple regression, just a regression, you know, it gets kind of crazy. Here's our model summary. Here's our R-squared. Look at that. Your R-squared, remember I said it was the amount of variance that your predictors are contributing to that outcome. It's like how much are those predictors contributing to the outcome is basically the way to look at it. And it is based on how far those errors are away from that line. But the reason we use it is we're going to say, gee, how good is this model? How well did those predictors predict that outcome? So here, those predictors predicted 80% of that outcome of the post-test score, which is pretty good. But that also means there's 20% out there that we didn't account for. So there might be some other measurement, some other type of predictor that may have contributed more. Thing you need to be careful about on these models too, on a regression model, is the more items you add in there, the higher your R-squared will get just because you're adding more predictors in. So if I put 20 predictors in there, you might get a 90% R-squared, which is great. You go, oh, I have a great model. It's, you know, these 20 predictors predicted the post-test stress score so well, 90% of it. Well, yeah, but it's just because you just keep throwing more things in. I always say you can throw in the kitchen sink, but is it useful? And so this is a good indicator of that. With 4 predictors getting 80%, that's pretty darn good. And your model significance, you look right over here at the ANOVA table. If it's less than 0.05, you have a significant model. Let's look down at the coefficients. This is the fun part. You look at this table here with the little b's, or it's a big B, I guess, and here's your numbers. These are the numbers that get multiplied by this number gets multiplied by your pretest score. This number here is going to get multiplied by age. This one here is going to get multiplied by the person's gender, and this one, if they're a female, okay? And here's our group, whether they're experimental or control. So I'll explain these in a little bit. But as you can see, you can just look at the direction of it. The constant really doesn't mean much. In these models, I'll show you if we have time. I don't know if we'll have time today. There's something called mean centering where you can make this constant, which is this is SPSS's name for the y-intercept. Okay, so there's a way to make this have more meaning. I don't know if we'll get to it today. But then you look over here and you see your significance. These are your p-values. So what you're looking for here is any of these that are less than 0.05. So I don't know how to get that to go away. There we go. So our pretest was significant. Our gender, females, were significant. And the group, the experimental group, was also significant because remember we coded females as 1 and we coded the experimental group as 1. So that's what these are relating to. So this is females as compared to males. And this is experimental group as compared to the control. Okay. Increases in age are associated with a decrease because it's negative, a decrease in the post-test scores. Also, if you're female compared to males, the score looks like it's going to go down by about 3 points for your post-test. So they're going to have less stress. And if you were in the experimental group, your score went down by about 8 points when compared to the ones that were in the control group. Okay, and that's what that's saying. This is saying for each, they make it sound so confusing sometimes. For each 1 unit increase in age, each 1 year increase in age, your outcome is going to decrease by this factor of 0.114. Okay, and really what you need to do is kind of look at this and say, okay, age for each year increase, it goes down, just like I was saying before. So those are things to look out here. Here's where you would look for multicollinearity. If this is in this one too, but I like this one's easier. For me, I know if this is 10 or above, I have some problems with the predictors. No problems today though. Okay, let's go back and look at our handout. I think we have some little more here. Oops. I'm going to show you that in a minute. Those are those residuals I was talking about. Okay, so we have the one table with the B values, these B's. What we're going to do is take these B's and we're going to plug them into our equation. So here's our model. There's our outcome, our post-test score. There's our intercept. And here's our B's. And then, of course, these will be our X's. Then the X1, what did we say? That was the pretest. This is age. This was gender. And this one was group, which group they were in. Okay, so here we are. Post-intervention stress. It's 0.67. So here's our little b from our other table. A negative 0.42, negative 3.92, and negative 9.01. And like I showed you, here they are in the table. Wait, did I do them different? How come I got different numbers? Where's our 2.98? Maybe I'm still looking at a different one. See, I tried to run it so I get the exact same numbers, and I got different numbers. So let's see what we got. Why did I do that? Why did I get 0.9812? Well, they're right here. Well, what did I do on this one? Okay, somehow I got different numbers. Darn, I was going so well too. Okay, well, let's look back at this. How would we do this? I will change the slide, but let's assume that the betas aren't these numbers, but they're these numbers that I put in. We have the 0.298. Then I have here a 0.67. I'll say was my B1 for the pre-intervention. 0.42 multiplied by whatever the person's age is. Then we're going to, and then that's going to be subtracted. This is going to be subtracted because the female scores went down lower. And a participant group experimental also is subtracted. Okay, we can see from the equation that Every 1 year increase in a participant's age decreases the post-intervention stress by a factor of 0.42, see? Okay. Females on average score about 4 points lower than males. And those in the treatment group that did get the intervention, the biofeedback, they scored about 9 points lower than those who didn't. Okay. So the estimates we make from the regression model are set up in a way that each of the coefficients are representative of the value that we multiply our predictors by. And this is holding every other predictor constant. So in other words, the B value from that column for a predictor is assuming that all of the other predictors went to 0. Okay, so it's like, how much does this contribute to the outcome if we pretend like none of those other ones were in the equation, even though we put them in. Okay, but that's what we call controlling. Here's an example. Participants in the experimental group, they scored about 9 points lower. At least that's what I reported, even though it didn't look like that in the output. Sorry about that. They scored about 9 points lower on their post-intervention scores than those who were in the control group, holding all of the other predictors constant, which means keeping them at 0. This means that participants in the experimental group scored 9 points lower on post-intervention stress when the pre-intervention stress score is 0. A participant's age is 0, and the participant is male, and also that when they're in the because compared to the control group, right? Because these are the ones that are in the treatment group. Well, this is fine. A pre-intervention stress score of 0 is fine. That's a valid score. A person can have a score of 0. However, in this study, nobody was 0. We didn't have any newborn babies. Okay, so that's where the constant, this constant term, this 2.98 or whatever number it should be, with this one that's here all by itself, the intercept, this is representative when everything is 0. Okay, well, in this case, we don't have any babies, so this is why I say a lot of times this constant term is not worth much. Okay, but let's talk about that a little bit more. I think I already talked about this. When all the other predictors are zeroed out, means a person who scored 0 on their pre-intervention and is a baby, is male, and was in the control group, they can be expected to have a post-intervention stress score of 2.98, because if that would mean that everything else is zeroed out. So it doesn't matter. It would mean that all these betas, assuming all these things were 0, well, anything you multiply, if this was a 0, that would turn this into 0, right? Because you're multiplying. So if everything, all these little b's were 0s, that would be your post-intervention score. So you wouldn't be all that stressed. I mean, if the range is from 0 to 56, 2.98 isn't all that stressed anyway. However, it doesn't make a difference because we didn't have any babies, right? So usually it's meaningless, but there's 3 exceptions. If all the predictors were dummy coded, it would make some sense because we just had the experimental group and we had gender, those 2 predictors, then that intercept would have some meaning. In fact, I don't know if we have time to try it, but well, maybe we will if we have some time. But so if they were all dummy coded, you'd be okay. The intercept actually would have some value. If the value of 0 on those continuous variables have a meaning, in the case of the pre-intervention score, a score of 0 is possible, that's good, then you're fine. Your intercept actually would have some meaning too, because you would have a 0 would be possible. However, in this case, age, that's where we're hitting our problem. So whenever we have something like that and we really want to maybe try to get our intercept to tell us something better, that's when we'll mean center. We'll mean center any of the continuous variables that can't have a 0. And so that would be age in our case. They shouldn't have a value of 0 because all the participants are adults. Okay, so it's very simple to do a mean center. You just find the mean value for your variable, in this case age, and you subtract it from all the observed values for each person. So I think we looked at it before. The mean age was 19.9. Okay, so what we're going to do is we're going to take that mean value, that average, and we're going to subtract it from everybody's age, and then we're going to make a new variable, and we're going to throw it in the model. Okay, so let's go ahead and see what we get. I'm going to show you how to do this really quick. Okay, so we'll go up to transform. We're going to compute a variable. Let's call it mean center age. Okay. And then over here, we're going to define it. So we're going to go down here. Oh, here's age. Okay, so we're going to take age, and we're going to subtract 19.90. And we're going to click OK. And let's make sure it's in the data. So we just go to the end of our data set. There he is. So it looks really weird, but what it did was it centered everybody onto that 19.90, which actually made that the zero. That became our new zero. So now instead of saying the age is 0, our model is actually going to give us results for somebody who's 19.90 years of age. Let's go ahead and run the model with that new predictor and see what we get. And you'll see the only thing that really changes is the intercept. So we'll go regression. We'll go to linear. So I have this basically all set up. So let's take out age. We'll move them back. And instead, let's put in mean center age. Okay. And it runs. And here we have it. Here's our new numbers. Here's our correlations again. Go back down. I think our squares, they didn't change. I think they should also, everything should be about the same. Okay. All of these coefficients are about the same. This is different. Okay. And our constant changed. Okay. So there's everything else, though, should have stayed basically the same. And if I put the right numbers in, you would see that. So let's go back in. I'm so sorry about that. Okay. So we did the mean centering. And when we run it, I somehow got this. Let me see, did I get that this time? So it said the constant was 4.71. See, it's different here. Okay, so I don't know what I did. Maybe I opened up the wrong data set. Okay, but let's go ahead and assume that our B values were actually these values. Okay, well now we have our new post-intervention stress score with a 4.71, and before I think it was 2 point something. And this is whenever you have people that are male, they're in a control group, and they're 19 years of age, 19.90 years of age. Then their post-intervention score, if their pre-intervention stress score was 0, their post-intervention score would be 4.71. Okay, and that seems kind of strange because you would think it would go down, but it's probably something about that pre-intervention stress score being a 0. It can't go down any further, right? So your post-intervention score's got to be something, you know, and it's really not taking that into account. So you might also want to consider doing the mean centering that pre-intervention stress score too, because that could be a problem. So we see that all the coefficients are the same. The only changes for the intercept. Okay, so in this model, the intercept term, which is your y-intercept, 4.71, now represents the average post-intervention stress score for a person who scored 0, 19 years of age, male, in the control group. And I know what you're saying. You're saying, boy, this is horrible. You know, nothing worked now. What you're saying is, hey, what about those two important assumptions? There must be a linear relationship between the predictors and the criterions. Well, that's in the model. We build it that way, right? The coefficients are just numbers. They're not squared. They're not multiplied together, and that's those B's, right? Now, we can have these X's, your X terms, your predictors, they can be squared. They can be multiplied together. They can, but it's just these terms out front, these things you're multiplying them with, these coefficients. Those can only be linear. And so here we have pluses and minuses, nothing going on that's strange there. So it is linear, okay? It's just a bunch of things added up to get an outcome, okay? Even though you're multiplying these little terms together, the terms are being added and subtracted. Basic algebra. Okay, now if we wanted to test an interaction term, we could, as long as it's a predictor, but not the B's. Okay, so that's good to know. You can't have this, you can't have that. Okay, here's our assumptions for number 6. When we ran those regressions, let's go back into the output. Just want to see if my model came out good today. We might as well. Here's the model we just ran where we put in the mean centered age. What we want to do is what do we say? They needed to be normally distributed. This is nice and normal. These are your residuals. These are your error terms, okay? And this is how far the errors were from that best fitting line, okay? As you can see, here's your 0, right? Some of your error terms were below the line. Some of your error terms were above the line. And 0 we're considering as the line, right? That's going to be where they go to. So that's nice. That's normal. That's good. That meets that part of the assumption. The normal plot looks pretty good. They're all along that line, and that's what you want. What this is doing is it's taking the distribution of those errors that are plotted here, and it's comparing it to what would be expected if you had the normal distribution. So it's basically comparing it to the normal distribution, and it gives you this. And what you want are all your little data points to line up on that line, and they're doing so very, very nicely. And then finally, this is the big one. This is the one that a lot of people like to look at. This is your scatter plot. You see scatter plot here of your residuals, of your errors. Okay, so again, here's your 0, which would be your middle, and you want an equal number of errors above it and equal kind of number of errors below it. You don't want to see any kind of weird shapes. A football shape is okay. But you don't want to see something, sometimes you'll see something that looks like a great big megaphone or something where it's real skinny here and real wide there. I don't really have time to show you today, but that's what you want, a nice scatter. Okay, so we're running out of time. I knew it would go a little long. But here it is in the output too. So, and there's our scatter plot. Everything is looking good. And it was looking good in the model I ran too today. So. Here's some references. We covered just the basics. There's so many concepts and intricacies of this. I love it. I think it's the greatest technique ever. I think it tells so much. But here you can look on the Handbook for Biological Statistics. It's a nice, easy read usually. Here's a link to that. UCLA website, you know I love that. Here's a link to that. If you want to use Excel for regression, you can. Here's something on YouTube you can watch. Karen Grace Martin at the Analysis Factor, I love her. She's great. She wrote something about mean centering you might want to look at. And I think she also used age, so that'll be interesting. Really quick, we have events. I probably won't go over all of them today, but I'll give you the PDF. We're just running out of time, so you'll have the PDF. You can read about these things. I do want to say that 2015 will be a spectacular year. If you have any questions, give me a call, give me an email, send me an email, info@omegastatistics.com or elaine@omegastatistics.com. I want to thank you for attending. Brianna, I'll bring you in real quick and see if we have any questions. What we might do is maybe answer them and send them out in maybe in an email or something like that. But let me see if I can bring Brianna in and check in and see how things are going with her. Let's see, I gotta find her. And there you are. Hello, Brianna, are you there?
I'm here. Hi, everybody.
So do we have some questions today?
Let's see. We did have a few questions throughout the webinar, but you ended up answering all of them. So.
Oh, okay. I didn't do that bad then, huh?
No. We even have people requesting previous webinars, so I think we did really good today.
Great. Okay. Well, you know what? If anybody here has any questions, feel free to shoot me an email or Brianna. Brianna is Brianna@omegastatistics.com or info@omegastatistics.com. It'll come right to me, and I'll be glad to answer them. And we'll get all this put together in a nice little package. And maybe you can run it and tell me where I went wrong with my numbers. But I want to thank everybody for attending and bearing with me. The neat thing about live events is you never know what's going to happen, and it really keeps me on my toes. So thank you, and have a great holiday, everybody. And thank you, Brianna.
Well, thank you.
Okay, bye-bye.
Bye.